Welcome back to our final lecture video on design verification and dynamic simulation. We have covered a lot of material in this course, from projections to solid modeling and engineering drawings, to mechanisms and our most recent topic of assemblies. In the last video, we discussed producing assembly drawings from assembly models, which is important for design documentation. In this final lecture video, we will focus instead on design verification, and particularly how we can perform dynamic simulations on assembly models in Inventor for this purpose. To start, recall that solid models are digital representations of parts that we can arrange together in assemblies to make a final device or a structure that will perform a specific function. There are a variety of reasons that we would want to use computer-aided design to make solid models or assemblies. Last week, we talked about using these models for design documentation, and another application is visualization and prototyping. For instance, 3D printing solid models has become tremendously popular in recent years. Assemblies can also be used to evaluate a design against spatial constraints. For example, CAD software gives us tools to check for interference between parts in a design, and these are all important aspects of design verification. But what about other aspects of design verification? For example, how do we ensure that a gear train design meets output speed and torque requirements? Or how do we verify that our L bracket, way back from the first video, meets the new load-bearing requirements? What about verifying if pump flow characteristics meet design requirements, or ensuring that appropriate heat transfer occurs in a shell and tube heat exchanger? These are all examples of additional aspects of engineering design that require verification. So how might we accomplish this? Well, the basis of a design likely begins with calculations that can be done by hand or via spreadsheets, so we could rely on that, but you can imagine that such calculations may become tedious, especially for very complex problems. We could also construct real 3D prototypes for testing, although that could be time-consuming, costly, and challenging, especially in iterative design. Fortunately, many computer applications have been developed to facilitate this design verification through simulations, and you guessed it, these simulations require solid models. For example, you can perform a dynamic simulation of a gear train directly in Autodesk Inventor to verify your output speed, and you could also perform a static stress analysis in Inventor for our L bracket example. Software for computational fluid dynamics for fluid flow and heat transfer analysis, such as the ones used to produce these pump and heat exchanger images, also require solid models to model the system, which goes to show that solid models and assemblies can be just as useful for design verification and analysis as they are for initial visualization and final documentation. In this video, we will focus specifically on the dynamic simulation application of CAD, which can be used to verify mechanism kinematics, and to do so, we will start off by reviewing solid model degrees of freedom. Recall from last week's video on assembly modeling that solid models have 6 degrees of freedom, 3 translation and 3 rotation about the principal axes. Last week, we discussed the importance of removing these degrees of freedom through the application of assembly constraints, which create dimensional or geometric relationships between instances of components in an assembly. We learned about 3 common constraint types: axial, mate, and planar relationships, and we learned about Inventor-specific assembly constraint options, which gave us the tools necessary to fully constrain an assembly so that it is incapable of any movement. But in reality, a lot of assembly models deal with mechanisms that are not meant to be completely immovable, hence why they're called mechanisms. For instance, we know that the plate of a door hinge should be capable of rotation for the door to open and close. So we still want to somehow constrain our assembly, but also enable this motion. Simply leaving degrees of freedom unconstrained is not sufficient in assembly modeling. Instead, we want to apply assembly constraints with limits. Doing so is actually not too big of a stretch from the process we learned last week in assembly modeling. Say we want to allow the motion shown in this simulation with the pin moving in and out and the top hinge plate rotating open and close. To start, with the pin constraint, we can apply a mate constraint that mates the bottom face of the cap of the pin to the side face of the hinge. But rather than just leaving this constraint as is, we could apply limits that would enable the mate offset to vary between 0 and 100 millimeters. This way, we still constrain the pin, but we have left some ability for the pin to translate within these limits, so there's still some degree of freedom remaining. We can do the same for the top hinge plate, where we apply an angle constraint between the top and bottom hinge faces, but now we will limit the angle to be between 0 and 180 degrees. Again, we have constrained the rotation of the hinge plate, but within set limits so that some rotation is still permitted. So applying assembly constraints with limits is one way for us to keep a part's ability to move in some defined way within an assembly. However, in the assembly of some mechanisms, we may also want the movement of one instance of a component to impose some motion on another. Consider this gear train as an example. If we left a rotation degree of freedom for gear C and its rod so that they could rotate, we would want the rotation of gear C to impose rotation on gear D, according to the gearing set ratio. For this, we need a motion constraint. While assembly constraints define positions of component instances within an assembly, motion constraints define how the movement of one instance imposes motion on another. We can apply a motion constraint to this gearing set in Inventor using the same constraint tool, but selecting the motion constraint tab instead. Two types of motion constraints that we can apply are rotation-rotation constraints or rotation-translation constraints, where the former is suitable for applications like spur gear sets, and the latter would be suitable for, say, a rack and pinion application. If we select the rotation-rotation type for this gearing set, we can select the two gears and define the ratio between them. Once this motion constraint is set, we can try moving around gear C, and we can see how gear D moves in response, which is quite fun. So, by applying assembly constraints with limits and motion constraints, we are essentially leaving some degrees of freedom remaining in our assembly, which allows us to animate it, as was shown in the previous slide. Animations give a good general idea of mechanism kinematics in operational mode, but such animations are inherently qualitative. If we want to perform a more quantitative assessment of a mechanism's design, we can perform a dynamic simulation, which models the time-varying behavior of a mechanism in response to some input, whereby virtual probes can be used to measure critical parameters over time. In the context of our gear train, we can perform a dynamic simulation where we set some input angular velocity profile and monitor the output gear angular velocity over time. Such dynamic simulations can also account for physical properties like mass, friction, inertia, and loading to provide a better understanding of how mechanisms would operate in the real world, which is very handy, but it can also be computationally demanding. For now, we will stick to a simple simulation of a gear train to verify that its output speed meets design requirements, and we will not account for mass or friction or inertia, so let's briefly go over the general steps for dynamic simulation. The first step is to create the motion constraints relating meshing gears in our gear train, which we saw for gear C and D already. Once those motion constraints are applied, this gives Inventor the necessary information to understand how an imposed motion on gear A causes motion in gear D. So the next step is to enter the dynamic simulation environment to set up our simulation. Once in this dynamic simulation environment, we need to insert joints between meshing gears. There are many different types of joints that exist, but for this gear train example, we will insert rolling cylinder-on-cylinder joints to again define how the motion of meshing gears are related. Once these joints are created, we can then impose a motion on the input gear joint, defining its angular velocity over time. Then we can go ahead and run our dynamic simulation to view the results. The joints also allows us to graph the velocities of the intermediate and output gears in our gearing train, which enables design verification of our output speed. In this case, we can see that the speed of gear D is greatly reduced. Here's another dynamic simulation of a gear train in a hand mixer, and yet another example of a vise, both modeled and simulated in Autodesk Inventor. So now we are aware that solid models are not only useful for visualization, prototyping, and documentation, but also for design verification through simulation. This lecture and the corresponding lab lesson gives you all of the information required for you to make a dynamic simulation of your project. Even though dynamic simulation was the focus in this video, on a bigger picture, we identified that solid models and assemblies are necessary for all sorts of simulations, and as such, they are important in all engineering disciplines. This wraps up our final topic of the graphics module, so congratulations for making it through all of the content, which we will summarize in one final review video.